In sections 10.2 and 10.3, we're going to be talking about a new coordinate system called polar coordinates. We're used to identifying points by giving their x and y coordinates, the distance how far over from the origin, and how far up. When we locate points using polar coordinates, we give the directions to that point in a different way. We measure everything still from what we would call the origin, sometimes called the pole in polar coordinates, but it's still just that origin point in the middle. And from O, if I'm trying to locate this point P, the first thing I do is construct this ray that goes from O to P. And that distance from O to P is called R. We say R is the directed distance from O to P, with positive being in the direction. OP. The next thing we're going to do is give a value for theta. Theta is the directed angle from what we used to call the x-axis, but we're now going to call the polar axis. It's the angle from that polar axis to the ray that we just drew. And again, we say it's the directed angle with positive being the counterclockwise direction. So, to give the coordinates of the point P in polar coordinates, it's no longer x comma y. We now give it in the order r comma theta. How far away from the origin and at what angle from the positive x-axis, now called the polar axis. There's something that's perhaps mildly inconvenient about polar coordinates, but as we press on, we're going to find enough good things about it that we're going to still want to use it. But here's the mild inconvenience. In rectangular coordinates, it was really nice that every point xy had a unique representation, right? The point 5,2 was always the point 5,2. There was no other way to write it. Unfortunately, that's not true with polar coordinates if we allow r and theta to take on any values from negative infinity to infinity. We're going to see that in the example of the point plotted below. First of all, let's take a look at this plot. This point is plotted on polar graph paper. You'll notice with polar graph paper, I still have my axes that I originally labeled x and y, but this is now really the polar axis. The circles or rings are all different r values, right? This first inner ring, every point on that ring would have an r value of 1 because the distance from the pole to any point on that ring is exactly 1. Similarly, this next ring, every point in that ring would have an r value of 2. All of these points are exactly 2 units from the pole. And then the point P that we're really interested in here is on the next ring out. And that ring, everything has a distance of 3. From the pole, we would come out 1, 2, 3 units. 1, 2, 3 to get to a point P. So, in order to write P, I'm going to start by saying the r value here would be 3. I now need to give a theta value, right? Just saying r equals 3 isn't enough because there's infinitely many points with r equal 3. All of these points around here all have r equal to 3. So the next thing I'm going to give is a theta value. I need to know what is the angle from this polar axis here, measuring positive as counterclockwise. So I'm really looking to give this angle right here. First of all, just in terms of kind of identifying the angle, notice that to go from 0, theta equals 0 here, over here to where certainly theta would be pi, I've split this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. So if these are all twelfths, this would be 1 pi over 12. This would be 2 pi over 12, 3 pi over 12, etc., all the way around. So my point right here lies at this theta value, which would, boy, I said 3 pi over 12, I don't know why I wrote 4, 3 pi over 12, 4 pi over 12, etc. So this would be 5 twelfths, 6, 7, 8, 9 pi over 12. For the theta value that I want for my point. I'll just reduce that to lowest terms. 9 twelfths would be 3 fourths. So I'm going to go with a 3 pi over 4 as my theta value. All right, now there are other ways that I could write that point. For right now, I'm going to stick with an r of 3, but I could think of the angle differently. I could, for example, choose to go all the way around once before stopping at that point. So now my new theta value is going to be the old value, theta value of 3 fourths, plus an extra trip around, 2 pi. So if I were to take my original theta of 3 pi over 4 and add 2 pi, which would be 8 pi over 4, I'd get 11 pi over 4 for that theta value. Now the point itself hasn't changed, right? I'm really still in the same location with my point P, but notice there are 2 different points I have now, both of which represent that same point. The polar representation of a point is not unique. Of course, I could keep going, right? I could have gone around here 3 times, or 4 times, or 5 times, as many times as I want, and I could have kept getting more and more new theta values. So right away, we've got infinitely many possibilities. There's another way to write P as well. I said that R was the directed distance, with the distance from the pole toward P being positive. I can also make that a negative distance. And the way that I do that is by literally pushing exactly the opposite direction across the pole. So instead of going out from the pole this way, I go exactly the opposite out from the pole this way. 1, 2, 3 units to right here. Because that's actually not in the same direction as P, but rather the opposite direction of P, we would consider that a negative value of R. So if R is negative 3, what are some possible angles that I could use? Well, we still start from the positive x-axis, and if I go around to that new line that I just drew, the r equal negative 3 line, that would be, see, that would be 1 or 12 twelves, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That is 21 pi over 12. If I reduce that to lowest terms, I would have 7 pi over 4. So that's one possibility. I could also choose to use a negative angle. I could have done like I did up here, right? I could have added more circles. That would have been fine. But another option would be to also use a negative angle. So I'm again going to go with the -3 radius line, R. And this time, I'm going to think of my angle as coming clockwise, or in the negative direction from the polar axis. That would be -1, -2, -3 pi over 12. Reducing that gives me -pi4. And once again, there are many, many other possibilities. I could go around multiple times in the negative direction before stopping here. I could go around multiple times in the positive direction before stopping there. So here are 4 different representations, all of which represent that same point P, and there are infinitely many more. That's not super convenient. Usually in math, when that happens, we decide to agree on one standard representation. Unfortunately here, we're actually going to have to agree on 2. There are 2 what we call primary representations of a point in polar coordinates. The 2 primary representations are the 2 representations that satisfy theta is between 0 and 2 pi. So if you're asked for a primary representation, you're only allowed to use thetas from 0 to 2 pi. For those 2 representations, one will have a positive R value, the other will have a negative R value. It's the only way we'll be able to get it to work. Okay? So we're going to go ahead and find the primary representations of the 3 different points on this graph. Let me start with this one right here. I'm going to call it A. The point A is 4 units from the pole, so R would be 4, and it's right on the polar axis. So one option would be to just let theta be 0. Now remember, this looks like it could be rectangular coordinates, right? 4, 0 also works in rectangular, but I'm thinking of this as polar. I'm thinking of this as an R value and a theta value. Because of that, I could also do another representation of A with a -4 for the R value. -4 would make this go in exactly the opposite direction. Right there. Just going to put a little X there. Exactly opposite of A. So R was -4. And you'll notice that the angle here is exactly pi. So both of those are valid representations of A. Let's go over here next. I'm going to call this one B. B is 1, 2, 3 units out from the pole. So my positive R would be 3. And if I want to know what angle that is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pi over 12, or 3 pi over 4. Another representation of B would have -3 as the R value, and that's going to be the one that's exactly opposite of B. So trace back through the pole exactly opposite, and then back out 3 units again would be right there. And that one, again, we've already said our B is -3, would have as its theta value, that'd be 12 twelfths, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 pi over 12, or in lowest terms, 7 pi over 4. And that's it. Only two primary representations. Those are the only two angles that work between 0 and 2 pi. All right, I've got one more right here. Let me call it C. C is 2 units out from the pole. So for my positive r, I'm going to use 2. And then I need to figure out that angle. Let's see, that's 12 twelfths, 13, 14, 15, 16, 17. There will be another representation of C with a negative 2 for an r value. Again, that'll be exactly opposite right here. So I need to know that theta value. Maybe 1, 2, 3, 4, 5. 5 pi over 12. So it takes just a little getting used to. We're not used to polar coordinates, but with a little getting used to, you should be able to find the two primary representations of any point in polar coordinates. All right, in our next example, gone the other way. I've given you one representation, and then I'm asking us to find the two primary representations and to plot the point. So, for A, and I'll call this point A, I've got the point 2 pi over 6. Since everything here is marked in twelfths, the first thing I'm going to do is just say that would be the same as 2 pi over 12. So I know I'm going to go out 1, 2. I'm on this line right here. And my r value is 2, so 2 units out from the origin on that ray. And there's my point A. That's already one primary representation, since pi sixth is an angle between 0 and 2 pi. So I'll get the other primary representation, the one that has a negative 2 for the r value. And that one will be exactly opposite this one, right here. And let's see, I need this angle. That's 12 twelfths, 13, 14 twelfths, which I could reduce to 7 pi over 6. So there are my two primary representations. All right, let's do this second one. I'm going to call this point B. This point is negative 4 comma pi thirds. So what does that tell me? First of all, pi thirds is the same as 4 pi over 12. So if I go to 1, 2, 3, 4 right here, the point that's 4 units out from the origin here is not the actual point. It's the reflection of the point across the pole. That's what a negative r value means. So the actual point B is exactly opposite that. 1, 2, 3, 4 units along the ray. And there's the point B. Again, I already know one primary representation, since that's an angle between 0 and 2 pi. I want the other one, the one with a positive 4 for r. And to get that, I will need this angle. So that's, this was 14, 15, 16 pi over 12. Or in lowest terms, 4 pi over 3. All right, hanging in there, let's keep going. We'll call this point C, 3 comma negative pi halves. I do have a positive r value, so this is the actual location of the point. Negative pi halves, like negative 90 degrees, that's down here, right? And we're going to come out 3 units. So there's my point C right there. Now this time, that is not a primary representation. My angle's not between 0 and 2 pi. So I used it to locate the point, but it doesn't count as a primary representation. First primary representation with a positive 3 for r would have this angle right here. That'd be 16, 17, 18 pi over 12. Or in lowest terms, 3 pi over 2. And then the other primary representation will have an r of negative 3. And that's going to be exactly across the origin, right here. So I need that angle. And of course that's 4, 5, 6 pi over 12. Or in lowest terms, pi over 2. All right, one more. We have our point D. R is negative 2, and the angle is negative 3 pi over 4, which, let's see, in 12, that'd be negative 9 pi over 12. So, going in the negative direction, I have negative 1, 2, 3, 4, 5, 6, 7, 8, 9 right here. And because this is a negative 2, this is not the actual location of the point. This is the reflection. 2 units out right there. So to find the actual point, I'm going to go ahead and follow this directly across the pole, out 2 units, and there's my point D. Notice again, this is not a primary representation. That angle is not between 0 and 2 pi. So for this point D, I'm going to give my first primary representation with a positive 2 as my r value. And then I need this angle. If that's 4 pi over 12, this must be 3 pi over 12, or pi fourths. The other primary representation would have an r of negative 2. We've already got it marked here, but I have to use a positive angle. So I need that angle right there. That would have to be 15 pi over 12. Or if I reduce that one to lowest terms, 5 pi over 4. So again, the geometry just takes a little getting used to, but there's some additional practice on locating and finding primary forms for these polar coordinates. All right, we are now ready to talk about the comparison or conversions between polar and rectangular coordinates. If you imagine your x-axis, which we're now calling the polar axis, and your y-axis here perpendicular to it through the pole, then for this one point, we've now got 2 different ways to represent it, right? If I'm thinking of rectangular coordinates, then how far over would be x, and how far up would be y. And we have our standard rectangular coordinates, x comma y. If I'm thinking in terms of polar coordinates, the distance from the pole to the point is r, and the angle from the polar axis is theta. Having x, y, r, and theta all in the same picture is going to allow me to write down some nice relationships between those variables. First of all, just looking at the picture, we clearly have a right triangle here, so I could write down the Pythagorean theorem for that triangle. X squared plus y squared equals r squared. That's one relationship. between some rectangular and polar variables. I'm also going to write down 3 of the trig relationships. I'm going to start with the tangent of theta. Tangent is opposite over adjacent, y over x. Then I'm going to write down the sine of theta. Sine is opposite over hypotenuse, y over r. And then finally the cosine relationship. Cosine of theta, adjacent over hypotenuse, would be x over r. Those 4 equations, which come right out of the geometry of the picture, will allow me to fairly easily convert back and forth between polar and rectangular coordinates. The first 2 equations are what I typically will use if I'm changing from rectangular to polar. So if I know xy and I'm trying to find r and theta, I'll usually use the x squared plus y squared equals r squared, and the tangent theta equals y over x. If I'm going the other way, if I'm starting with known polar coordinates and I want to move to rectangular, I'll use slightly modified form of those bottom 2. All I'm going to do is multiply the r over. So this says y equals r sine theta. And this one would say x equals r cosine theta. So let's use these equations to do a little converting. We've got some polar graph paper at the bottom, and it says to plot the point in polar coordinates and then find the corresponding rectangular coordinates. So this first one, r is 5, and theta is pi sixths, which I could think of as 2 pi twelfths. So on my polar graph paper, I'm going to go out all the way here to a radius of 5, and then 1 2/12. It's going to put me right there. Call that A for part A. All right. I now want to find the corresponding rectangular coordinates. So I've got my 2 conversions. X equals r cosine theta and y equals r sine theta. My r and theta are given to me in the rectangle or in the polar coordinates. So I'm just going to plug them in. R is 5 and theta is pi sixths. And by the way, just wanted to mention, you may know these really well, which is great. If not, here's a unit circle, right? We can always look them up. For pi sixths, cosine is the square root of 3 over 2, and sine is 1/2. So cosine was square root 3 over 2. Sine was 1/2. So I just get 5 square root 3 over 2 and 5/2. And so my rectangular coordinates are now right there. And notice what that's saying is that if I were to locate that point by going over and up, I'd be going over 5 square root 3 over 2 and up 5/2. Let's do a couple more. The second part, part B here, gives us the polar point, -3, 5 pi over 4. So watch out, here's that negative radius again. 5 pi over 4, that would be 15 pi over 12. So let's see, 12, 13, 14, 15 right here. 14, 15. But since the R value was -3, this isn't the actual point. It's the reflection of the actual point. The actual point is exactly opposite. Still, was it 3? Yeah, 3 units out. So there's B. All right, I'm going to use the exact same equations to convert to rectangular coordinates. So x would be r cosine theta. That would be -3 cosine 5 pi over 4. And y is r sine theta. That would be -3 sine 5 pi over 4. For 5 pi over 4, right here, both the cosine and sine are -√2 over 2. So I have negative times negative would be positive 3 square root 2 over 2 for both x and y. And so there's my point in rectangular coordinates. And again, just a reminder of what this is saying. It's saying that if we wanted to locate this point B in the rectangular coordinates, I would go over 3 square root 3 over 2, and then up 3 square root 2 over 2. All right, we've got one more. C is the point 2, negative pi thirds. I'm going to think of that in twelfths, so -4 pi twelfths. So let's say I come out to a radius of 2, and this time the angle's negative, so I'm going to go clockwise. 1, 2, 3, 4. The R value is positive, so this is the actual point, C. So converting, x would be 2 cosine negative pi thirds, and y would be 2 sine negative pi thirds. Let's see, negative pi thirds would be down here, same as 5 pi thirds. So the cosine is 1/2. The sine is negative square root 3 over 2. So I just get 1 for x and negative square root 3 for y. And those are the coordinates of my point in rectangular coordinates. And again, notice that makes sense. In rectangular coordinates, we'd go over to the right and then down a negative y value to get to C. All right, let's go the other way. In example 3, I'm now giving you the rectangular coordinates. When I say Cartesian, that's just another way of saying rectangular. And we want to find the polar coordinates both primary representations. All right, so our first point is 5, 5. And I'm going to make just a quick little diagram here. Right there. And I'm going to start by converting to the polar coordinates. Okay. I now use the other two equations. X squared plus y squared equals r squared, and tangent theta equals y over x. So I was given rectangular coordinates, so this is x and y. Plugging in, I would have 5 squared plus 5 squared equals r squared. 25 and 25, so 50 for r squared. R would be plus or minus the square root of 50. What's that? Plus or minus 5 square root 2 for r. And notice that's normal, right? For our two primary representations, one has a positive r, the other one has a negative r, so no surprise. All right, tangent theta equals y over x. So tangent theta would be 5 over 5, or 1. What angle has a tangent of 1? Well, it actually occurs twice. Tangent, remember, is sine over cosine. So right here, square root 2 over 2 divided by itself would be 1 at a theta of pi fourths. And it happens again down here, right? Negative square root 2 over 2 divided by itself would also be 1, down here at 5 pi over fourths. So we got theta equals pi fourths or 5 pi fourths. Keeps my theta between 0 and 2 pi, so those will be the two answers that we'll give. Now it's just a matter of matching them up. The positive r goes with which theta, and the negative r goes with which theta. And this is where my diagram comes in. This is a quadrant 1 point, so the positive value of r is going to go with this smaller angle, pi fourths. So we'll say positive 5 square root 2 goes with pi fourths, and negative 5 square root 2 is going to have to go with the 5 pi fourths. And again, that's going to be the one that's exactly the opposite over here. Right? That would be the negative r value. And that's the 5 pi over 4 angle. Let's do one more like that. In part B, again, we're given a point xy in rectangular coordinates. And again, I'm just going to do a quick little diagram. May or may not be super accurate. The main thing is I want to get it in the right quadrant. So I'd have 5 square root 3 over 2, so x would be positive. And the negative 5 halves, so y would be negative. And there's my point down here in the fourth quadrant. All right, we're going to do the same thing, same two equations. X squared plus y squared equals r squared. And tangent theta equals y over x. That would be 5 square root 3 over 2 squared plus negative 5 halves squared equals r squared. 25 times 3 would make that 75 over 4. And that would be 25 over 4. So I have 100 over 4, or 25. for r squared, meaning my r will be plus or minus 5. Tangent theta equals y over x. Y is negative 5/2 over x, 5 square root 3 over 2. If I just multiply top and bottom by 2 to cancel out those denominators, tangent theta is negative 5 over 5 square root 3. And I can cancel the 5's as well. Tangent theta is negative 1 over the square root of 3. Let's see, where would that be? Y over x, sine over cosine. Looks like it would be right here, right? If I take this divided by that, the 2's will cancel out, and I'll have negative 1 over the square root of 3, which is exactly what I want. So I'm thinking 11 pi over 6. Or, we kind of know now it's going to be the one right opposite, but let's take a look right here as well, right? Again, when I divide, the 2's are going to cancel out. So I'd have 1 divided by a negative square root 3. So 5 pi over 6 also works. All right. Which goes with which? This is a fourth quadrant angle. So the positive r value is going to go with this angle. The large one, the 11 pi over 6. So I'll have positive 5 going with 11 pi over 6, which by process of elimination means the negative 5 must go with the 5 pi over 6. But again, if you think about it, it makes sense. We went directly across. This would be our negative r value. And that would be that second quadrant angle, which is the 5 pi over 6. So, mostly it's algebra and arithmetic here, but there's a little geometry involved going this direction. We have to think about the quadrant, so we pair up the correct r with the correct theta. All right, that brings us to the end of part A here. We'll come back and continue to talk about polar coordinates in our next video.